So today we're going to look at how a new kind of AI is basically being taught to tame the ocean itself. This is an amazing story about tackling one of the biggest, most mind-boggling engineering challenges on the entire planet: how to keep these massive, massive structures from literally being swallowed by the sea. And really, that's the question at the heart of it all. Just picture a skyscraper. Now imagine, instead of building it on solid ground, you plop it down right in the middle of the ocean, where it's just getting hammered by waves day in and day out. How on earth do you keep that thing from toppling over? To even begin to answer that, you have to appreciate the sheer scale of what we're talking about. I mean, these aren't just some small rigs. These are true giants of the sea. And keeping them balanced is a constant, high-stakes fight against the raw, incredible power of the ocean. Look at that number. Yeah, that's almost 8 million kilograms. That's over 17 million pounds. That's the actual weight of the offshore platform they're studying here. Just try to imagine the unbelievable force it would take to move something that massive. Now imagine the force you need to keep it perfectly still. So the main tool that engineers have in their toolbox for this job is something called an active mass damper, or AMD. The easiest way to think about it is like a giant moving counterweight inside the platform that shifts around to cancel out the push and pull of the waves, actively working to keep the whole thing rock steady. Now that system works great, until it doesn't. What happens when the very piece of machinery that's designed to keep everyone safe suddenly breaks down? Well, this is where a huge problem gets a whole lot more complicated. And it's such a critical question, right? Because when you're in an environment this hostile, you can't just call a repair person to come right out. If a key component in that stabilization system fails, the situation can go from bad to worse fast. The technical term for this is an actuator fault. An actuator is basically the muscle of the system. It's the part that does the actual moving. So if that fails, the active mass damper can't do its job, and the platform's stability is immediately at risk. And that's the scary part. Just one little mechanical failure can trigger a chain reaction, turning what should be a manageable problem into a full-blown crisis. So the real goal here isn't just about finding a system that works, it's about finding one that's tough enough to handle the unexpected. Okay, and this is where things get really cool. This is where the new research comes in. Instead of just trying to build a better, stronger machine, engineers are now teaching machines how to think, how to adapt all on their own using a very specific type of AI. The technology that's making this all possible is called reinforcement learning, or RL for short. It's a type of machine learning where an AI basically learns by doing. It tries different things and it gets feedback, either rewards for good moves or penalties for bad ones. Honestly, the best way to picture it is like you're training a puppy. You tell it to sit. If it sits, it gets a treat. That's a positive reward. If it doesn't, well, no treat. Over time, it learns the best way to act to get the most treats. The AI is doing the exact same thing, just learning the perfect control strategy to maximize the platform's stability. And check out this quote from the research paper, because this is a total game changer. The AI method does not need the complete knowledge of the offshore platform. Just think about what that means for a second. In the real world, things rust, they wear down, they change in ways that aren't in the original blueprints. This AI can adapt to how the platform is today, not just how it was designed on paper. All right, so the researchers had this amazing idea, but they had to prove it works, right? So they set up a virtual showdown. They pitted their new AI system against a very advanced traditional controller to see how they'd stack up. So in one corner, we have the old guard, a really sophisticated but traditional control system. And in the other corner, the new challenger, the adaptive, AI-powered reinforcement learning controller. Let's see who came out on top. Okay, so first round, stability. This chart shows how much the platform was moving around even with a simulated failure. Now, a lower number is better here. And as you can see, they performed almost identically. So round one, it's pretty much a tie. They're both fantastic at keeping the structure stable. But this is where the story gets absolutely incredible. This chart shows how much energy, or control force, each system had to use to get that stability. The conventional method, you can see it used a good chunk of force. But then look at the AI method. It's just a tiny sliver in comparison. Let me put a number on that for you. The AI achieved the same level of safety, the same level of stability, while using 83% less energy. I mean, that's not just a little tweak. That is a massive, massive leap forward in efficiency. So what's the real payoff here? What does this incredible jump in efficiency actually mean out there in the real world? Well, it's about a lot more than just saving some money on an energy bill. It's really a triple win. First, obviously, it uses way less energy. Second, it's just more robust. It handles those real-world changes to the platform way better than the old system. And third, it can operate without needing a perfect blueprint because it's always learning and adapting on its own. And at the end of the day, that's what matters most. An intelligent system that uses less energy, puts less wear and tear on its own parts, and can adapt to changes as they happen is fundamentally a safer system. And in an environment where failure is just not an option, that adaptability is everything. It really gets you thinking, doesn't it? If this kind of AI can be this good at taming a giant in the middle of a raging ocean, just imagine what else it could do. Stabilizing our power grids, managing complex robotic surgeries, maybe even navigating spaceships through deep space. What other impossible problem are we going to teach it to solve next?